Alright, so earlier we had a discussion on what is the general workflow when you are working with CFD problems, right? Today we will be looking at, we will be going ahead with the discussion, and we will be creating a parametric model of a fan, and we will see, how you can control the different aspects of the fan, and automatically generate a CAD model without actually having to go in and remodel it by just changing a few variables around. You can get a completely different design and a different profile. So let's start it. Today we'll be using Salome, but this capability of parametric modeling is generally available with a lot of software packages. So SolidWorks has it, FreeCAD has it. I'm pretty sure Inventor will also have it. I'm not sure, I haven't used that as much, but yeah, in general, modern CAD softwares come with this parametric modeling capability. What that looks like, we will see right now. So in Salome, you have a bunch of tools. As you can see, in fact, it's a complete suite. You can do your your CAD modeling, your meshing, and your CFD in a single software without ever having to go anywhere else. But today we want to actually see, if you're working with different pieces of software packages, how do you connect these? And maybe you just don't like Solver Lab, maybe you prefer TCFD, or maybe you have some other software package that you like to use, and you just want to use Salome for its parametric modeling capabilities. Or maybe you have FreeCAD as your parametric model, and then you're using Salome as your meshing software. Or maybe you have something else as your meshing software, and then you're using Salome as your CFD solver, right? So let's go into the shaper module. Now when you load it, first things first, let's save the file, right? So if I just go to CFD demo, let's create a new folder, and let's call it Salome demo, and save the file as parametric fan, right? The design, we will keep it simple today. We won't be parameterizing every single aspect of the design, just to sort of make it easier to understand what's going on. So let's begin with starting a sketch. I like to draw in the y-axis plane with z-axis coming out of the screen. So let's start there, set plane view. Let's first of all create a circle. This will be our center hub for the fan, right? And let's define the radius to be something. Salome by default doesn't have units, basically because mathematically, it doesn't matter what the unit is, the model remains the same. So, but if you want to define the units, you can basically go into properties, select, let's choose millimeter today. So 20 millimeter, it's a 2 centimeter hub. We're building a small tiny fan, right? So this is good. Let's save that. Let's create the hub first, and you can see when I select the extrude, I've gotten something coming out of the surface. I can decide its length, let's make it 20, and you can earlier, it wouldn't automatically select the base normal, but now it has. But still, I would just go ahead and select the OZ axis, just to sort of be clear with it. So now we have a hub. That's great, but that's not the important part, right? The important part is the blade. So how do you go about designing that? Well, let's see. The blade, let's say we will design in the YOZ plane. So we need to create another plane where we can actually sketch the base for the plane. So I just create a new plane. I select the YOZ or ZOY plane. It's at 10 millimeter. Let's put it at 40 millimeter. And while we are at it, let's create another plane that's at let's say 25 millimeter, 30 millimeter, let's say. We will see how we will be using this one soon. So YOZ plane again, we select why. All right, yeah, this is it. Right, cool. So let's go to plane 2 first, and let's hide the first plane. Alright, so this is just plane 2, so we're looking at plane 2. Yeah, it is. Yeah, so plane 2 we created later on. This is plane 1, just to be sure, I will just check everything's fine. Yeah, just one thing, it's a good idea to name things while you're doing that. So we created a first sketch. You press function F2 to directly name it. Let's say hub sketch, and let's rename it as well, hub sketch, and let's give it a prefix of p to define that it directly falls in the part category, not under the construction category. So alright, just to sort of keep things understood. And plane 1, plane 2, this is plane 1, this one is the further one. So let's name it a plate plane, because this is the plane which we will be trying our plate. Let's name this one joint plane. Here we will be designing basically a circle that connects this hub to the plate using loft. We will see how that works in a bit. Now anyways, select this plane, set normal to get normal to it, and just to sort of here it is. Anyway, so in this plane, by default is it's very hard to see things on it, so we will just adjust the transparency a bit, so it's a bit easier to work with. Again, we go ahead and select this. Now what we can do is that we can start sketching. Select a line. Before that, I want to turn off the automatic constraints, because at least I sometimes have problem when it sort of snaps to some sort of constraint and I don't know what it is, and it breaks the constraint that I'm actually trying to put on. So it's going to turn that off. We will also define the length right now. So let's it's a completely arbitrary length for now, but we can change that later on. It doesn't matter for now. Let's draw another line, and let's make this auxiliary as well. Great. Now let's draw a few circles. One circle here, going to be auxiliary. Save it. One circle here, again going to be auxiliary. Let's define some auxiliary radii on these things. This will come handy soon. You will see how we're going to use it. So what we're trying to do right now is basically create a profile that looks like an aerofoil, right? We're not going to be exact with the design today. The goal is to just get something that resembles a generic fan blade. So that's why, but still we will try to make it look like, instead of making it a completely straight board or something, we will try to make it look like a Naga airfoil, right? So we've got something. Let's define the radii of this circle. They are completely free right now, but let's make it pretty small, 0.5 or something, and save it. Again, define the radii of this thing, make it pretty small. This one is smaller, so this will be the trailing edge, so that's why it's just a bit smaller. Let's get back to the view, and now we have got something. As you can see, if I just grab this point, I can if I just sort of grab this point, I can move things around, right? this is what degrees of freedom mean, right? I can play around with it, and everything else will change accordingly if it's constrained properly, and if it's not, it will change however it needs to in order to maintain the maintain the constraints that are already defined. All right, so I've got something. Let's create a profile that looks like an airfoil, right? So let's use B-spline for that purpose, and do this. Now I didn't just directly didn't connect these 2 points because in earlier I had issues. In general, if you when you're doing B-splines, for some reason it would snap to the places I didn't want it to snap, and the geometry would break sometimes. So it's just better to manually define the constraints. It's not a big issue. It's it's not a big problem to deal with. It's just a minor issue. So anyways, again you need to use coincident constraint. You select the points you want to constrain, select that, and look, we already have something that sort of resembles the upper surface of an aerofoil, right? And going further, let's create some points. One point here, and one point here. We will see how we will use this in a bit. I don't know, maybe we will need to make it 10 coins and stand as well, so it stays on the circle. Just to be sure, I'm going to apply the constraint, even though it seems like it is already constrained on it. I would prefer to manually define it still, just to be sure. Alright, so that works. We're getting pretty close to it. Now let's instead of a B-spline on the bottom, you can use a B-spline. That way you can also completely define the bottom profile of the airfoil, but to keep things simple, we just use a line and connect these 2 points. Yeah, that works. We will further constrain things. We will make this line and this line perpendicular, and we will make, so basically I'm making this line a tangent to this auxiliary circle. That's what the definition of a tangent is, right? It's perpendicular to the radii that is passing through the intersection point. Basic math. Anyways, going back, we have something that is pretty close to an aerofoil. These things, but as you can see, it's still quite changeable, so you can generate different kind of airfoil profiles. Now, this is not the correct way to do it, obviously. If you really wanted to design an aerofoil pretty specific to the use case, there are better ways of going about it. One of them would be to just go to NACA airfoil database, download the data points that define the NACA airfoil, import them into Salome, and use that to generate the profile. Or even a better way to use perhaps can be OpenVSP, which is an incredibly powerful software, completely free of cost. And you see, I've just generated a propeller here. As you can see, I can control different chords, the length, the number of plates. It's an amazing tool built by NASA. You can design the entirety of an aircraft in here. Not only that, it comes with inbuilt meshing capabilities, along with CFD capabilities. And as you can see, this wrote at the default aerofoil profile that it has. I've already gotten the values for a bunch of parameters here. I can go to the blade section, and I can, design something completely on my own. I can input data from some NACA airfoil. I can sort of define the profile of the blade in a very granular way, and control each aspect of it, and export them as a script, as all sorts of formats. So this is a really powerful tool if you are actually designing some sort of propeller for some purpose. But today the goal here is to just go over the basic of parametric modeling, and not to actually design this for any practical purpose. So that's why we will keep the design rather simple. Now, okay, so I don't like the fact that there's this break. It's not good. I want this to be a tangent to this curve. So before I go ahead and make it a tangent, what I will do is that I will create an arc like this. Great. And just to be sure that nothing breaks, I'm going to make sure that these things, I've already defined it as a constant point, so that should be fine. Just going to go ahead and do something similar on the trailing edge. This is good. Let's save it. All right, so now what I can do is that I can go in here, I can choose this tangent, make the controlling line for this B-spline tangent to this thing. So this angle here can change to whatever it wants to in order to accommodate this constraint. All right, plane, and again I go and do the exact same thing for the front. I select the line, I select the curve, and just like that, it's a constraint. Now, what will this lead to? Now this curve, it can still be controlled. You can still define the maximum chord length, but a bunch of things have been constrained, right? I can change the angle and stuff. Now, so this point can vary independently with respect to this point, not completely independently. It's a triangle if you look at this, and there are some mathematical constraints already there, but in general, it can vary a lot. So we will go ahead and restrict that a little bit too. So what we will do is that we will again take a line, draw it to this line, and make it auxiliary as well. Why? Because we will be extruding this profile, and we do not want this line to be extruded as well. So we want this thing to be perpendicular to this line. All right. So again, I constrain something, and now I can do this, right? But now I can define the length of this thing and really sort of put a hold on how much things can vary. It's 4.5. Let's make it 4. All right. So now we have gotten something that looks like an aerofoil, right? It's not completely constrained. So the way you can know that if something is completely constrained or completely defined is that these red lines will turn green. We don't need to completely restrict everything. We'll let some things vary. It's fine. It's for the demonstration purposes. But we will, however, positions are played at a specific place. So like this. Great. So again, as you can see, this thing is varying, and what we can do is that we can select this and we can make it vertical, right? And we could have also made a radii, from here to here, to make sure that this curve, the radius of this curve doesn't change much, but it's fine for now. So we've gotten a few things going on. All right, this is good. Let's create another line like this. Okay, I don't know if the point connected or not. I don't think it's connected. So we'll just try it again. Use auxiliary line. Define it as horizontal because we'll be using it to define our angle of attack. Now I just choose the angle dimensioning, and now I can do something like this, and I can make it 45 degrees or whatever, or I can make it 25 degrees to further restrict the things that can change. Perhaps we don't need more constraints, it should be fine, but just to sort of see how things are, let's close the help panel and let's change things around it. That's what happens if I do 45. So the blade just extends a little bit, and what if I do 60, right? So it accommodates the constraints automatically. Now let's go back to 25, and let's put a constraint on the length of this entire thing. So I can just turn the help panel on, and I can just use the length from here. Let's make it 25 or something. This is it, and it's constrained, and that's it. Now if I change the angle, you see the angle changes, but nothing much else happens. What else can be done? Do we want some other parameters to be changeable, but for now I guess this should be enough. Let's make the blade, no, this size seems fine for our purposes at least. So right, save this. So this prepared our sketch. This is pretty much done, so we save that. That's good, that's great. For now let's just hide the sketch, but rename it. Blade sketch, right? And this was our plane 1, so we'll also name it blade plane. Do the so right so this is it, blade sketch. That's good. All right. So we still have something, this thing, plane 2 and joint plane. So let's first of all rename this as well to joint plane, and then we will create a sketch to basically join this foil to sort of the base of our entire thing. Just gonna take a break here.